Warning! The video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we're going to continue our conversation about logarithmic functions, specifically graphs of logarithmic functions. So you need to have a strong familiarization with logarithms in general. You have to know their domains, all that fun stuff. So I'll read this out loud and then we'll hop into it. From our previous work with inverse functions, which is in the textbook I use, section 2.7, but you could just look at any of my videos that mention inverse functions. And the fact that f of x is equal to log base b of x is the inverse of g of x, which is b to the x, we know that the graph of the logarithm is a reflection of the exponential function about the line y equals x. That is, every time that you're asked to graph the inverse of a function, so if somebody hands you a function, they say graph its inverse, all you really need to do is reflect that function about the line y equals x. Let me showcase that here actually, because I think it's worthwhile. I'm going to use the color blue for this. And so if I were to graph, which one am I graphing here? Log base b of x. If I were to graph b raised to the x, it would look like this. Okay. And it would never actually touch the x-axis, but it would skyrocket up. It goes through 0, 1, and then way up here, it goes through 1, b. Again, if this is y equals b to the x. And if you want to graph the inverse function, I'll just do it like this, then you would reflect that picture about the line y equals x. And that's essentially what we've done. I mean, I haven't done it to scale, but that's exactly what we've done. Notice I've swapped the points. Instead of going through 0, 1, the inverse goes through 1, 0. And instead of going through 1, b, the inverse goes through b, 1. This logarithmic graph here, I cannot tell you, I cannot express how important it is that you know this logarithmic graph. A lot of people don't realize how important logarithms are. They are super duper important, and you just have to know the behavior of the logarithmic function as x approaches 0, as x goes to infinity, all that stuff. Notice as x gets really close to 0 for the logarithmic function, as our x values get closer and closer to 0, the corresponding y values get lower and lower. So if I plug in, for example, this x value, its y value is right here. The next x value lower to that, the y value is even lower. If I get really close to 0, the y values start rocketing down very quickly. So as x, this is what we say, as x approaches 0, well, it can't just approach 0, so we have to say it like this. As x approaches 0, but it's still positive, that's what that means, the y values, or the function values, approach negative infinity. You can see them dive down. It's really actually kind of hard to see on this graph, but it is diving down to negative infinity. It just goes down forever. So that is a critical skill you're going to need in calculus. Cannot express it enough. I'm telling you, it's so super important that you know that. So let's go ahead and graph some logarithms. And I don't pull any punches here because you have already graphed logarithms for quite some time. And so I immediately go for the throat. That's what I call this, going for the throat. So let's go ahead and graph this. Now, if those were parentheses, which they are totally not parentheses, but if those were parentheses, that would be the log base 2 of x minus 3 plus 1. And that minus 3 would shift the logarithmic function right 3 units. And then the plus 1 would shift the logarithmic function up 1 unit. That's what I'm actually going to start with. I have this logarithmic function. It looks like this, like every logarithmic function pretty much does. By the way, you will see people in a textbook, they'll say, oh, but logarithm base 1/2. It looks different. It's a decreasing function. To be honest with you, bases that are less than 1 are incredibly rare. So I don't really focus on that in a lecture. I deal with mostly bases that are greater than 1. So this is like base 2 on this log. So just to let you know, if you're in somebody else's class, they might, for some weird reason, ask you to deal with bases that are less than 1. And I wouldn't argue with that. I would say, okay, but that's not going to happen. You're always going to have bases that are, or I should say almost always, have bases that are greater than 1. Anyhow, if this is log base 2 of x, let me write that, log base 2 of x, then it goes through 1, 0, and later on it goes through 2, 1. I had to think for a second. My scale is not perfect, but whatever. All right, now what I'm going to do is just shift things right 3 units, which means I have to keep track of this vertical asymptote that every logarithm has. I'm going to shift everything right 3 units and then up 1. So here's my x and y axis. I will move the vertical asymptote over 1, 2, 3 units. So that's x equals 3. And I will just copy my logarithmic function, but I will plot points here. So this point was at 1, 0, but it's been moved to the right 3 units. So the x value is now 4. And the y value has increased by 1. So that's 4, 1. And the other point, which was at 2, 1, is now at 5, 2. 5, 2. So we'll say it's right about there. Otherwise, I think we're good. We'll go ahead and graph that. Trying to be somewhat careful here. There we go. Really nicely done. All right. But here's where you start saying that was not actually the log base 2 of x minus 3. It was a log base 2 of the absolute value of x minus 3. And here's where we're going to have a little side conversation. The side conversation goes like this. If I asked you to graph x, okay, you would say, easy breezy, I've been doing that for years. Yay, totally done, right? And then if I said, nope, never mind, I'm sorry, that's the absolute value of x. Well, you know, the absolute value of x just looks like this. It takes the picture that's on this side and reflects it about the y-axis. That's really what that absolute value is doing. A lot of people will say it takes these negative y values and flips them up. And that is kind of true. But in reality, how we're going to deal with it is it's going to take that rightmost picture and rotate it about the y-axis. Now you could do this with any function. So what if I took y equals the square root of x, which you know looks like this, and I said instead, oh, never mind, I want the absolute value of x. Notice the absolute values are in the inside of the function, inside of the square root, just like the absolute values here are inside our logarithm. Well, think what happens here. Does it take the negative numbers that are down here and flip them up? No, there were no negative numbers to begin with. So flipping things up does not make sense. However, before when we plugged in 1 to the square root, we got out 1. Now we have the option to plug in -1. The absolute value of -1 is +1. Square root of +1 is also 1. And you could do that all day long. You would get this. Again, it's just reinforcing what I said a moment ago, which is that it reflects your curve about the y-axis. You can do this with all different kinds of functions. So let's just create a function here. Let's create e to the, I don't care. It doesn't really matter, but let's just, let's say it's x minus 2. Okay. Oops, except the -2 is in the wrong spot. So I'm going to put it in the numerator, which means I have to put parentheses. There we go. X minus 2. There we go. Now, the argument for that function is not x, it's x minus 2. That's the argument for the exponential piece of that function. If I put that in absolute values, absolute and absolute, notice what it does. It reflects about what we would consider to be its anchor point. Why do I know that's its anchor point? Well, let's take a look at e to the x itself. Let me get rid of the absolute values. If I had initially, before I did any type of shift, thrown the absolute value on there, it totally does rotate that function. So pre-shift, you would rotate that about the y-axis. And that's exactly what's happening. You could do this with any type of function. So the punchline here is, if you have a function and its argument has an absolute value on it, you always reserve shifts and transformation, or shifts specifically, to the last step. And I've been saying that since the beginning of this course when we did transformations early on. Shifts are always the last thing you want to do. You apply vertical stretches or compressions, you apply horizontal stretches or compressions, you apply reflections, all that stuff before you do your shifts. So if we wanted to look at, for example, the sine, and I'm going to turn off, let me just type that and then turn off the graph. Let's say we want to look at the sine of the absolute value of x minus 2, for example. Let's say that was our ultimate goal. The way that I would do that is not do the shift first. I would say, well, let's graph the sine of x. There it is right there. And now I'm going to erase the stuff that's on the left-hand side here, and I'm just going to reflect the positive bits. When I say positive, the stuff on the positive x values here, I'll reflect all this stuff about the y-axis. So here I go. I'm about to reflect about the y-axis. And do you see that that's exactly what happened? That is a reflection about the y-axis of the sine curve starting at x equals 0 and going to infinity. So I start with that, and then I apply the transformation. I'm going to grab this point and I'm going to move it over 2 units to the right. So it'll be somewhere around, I don't know where 2 is on this thing, but oh, I was actually right at it. So it's going to be somewhere right about here when I put the minus 2 on there. And watch what happens. Yep, that's exactly where it is. So I do the reflection about the y-axis of the positive part of the graph. I shouldn't say positive part of the graph, but the graph pertaining to positive x values. I rotate about the y-axis to get the absolute value, and then I move that over 2 units. That's exactly how you would do that. So shifts always last. And when I say I take the absolute value, I'm really taking the absolute value of the argument. If I took the absolute value of the sine, that's a completely different picture that we'll deal with in a moment. So all that being said, all I really need to do is go to my original base graph and say, okay, I'm going to take the picture to the right here, and I'm going to reflect it about the y-axis. So this, what you're looking at here, is now the log base 2 of the absolute value of x. And now all I need to do is shift it to the right 3 units and up 1, and you will have the actual graph of the log base 2 of the absolute value of x minus 3 and then plus 1. It's a really nice way of doing that. Very cool idea. So absolute values on arguments, not on functions, but on the arguments of the function, reflect about the y-axis. It only reflects the function for its positive x values. Okay. Notice that the domain of this logarithmic function is not just all positive numbers. The domain of this function is all numbers not equal to 3. So negative infinity up to 3, union 3 to infinity. It's a rare circumstance where the logarithm has a domain that extends in both directions. Believe it or not, this is actually a simpler question. A lot of students do fine on this. Now we know, just from our previous work there, that the graph of that logarithmic function in general just looks like this. And I'm not plotting the points now because I'm just quickly sketching this out. It looks like this. However, at the end of graphing all that, the very last thing you're going to do is apply this absolute value. And in that case, it takes all the negative y values, all these guys right here, and it forces them to be positive. So if I'm being exact about this, let me go ahead and let me graph this really nicely. So, or at least better than what I just did. Okay, so we have something that looks like this. I'm not saying this is exactly correct, but this is good enough. Okay. And if we're about to take the absolute value of that function, it means that whenever the function goes negative, it should actually be written as positive. So it's going to look like the following. I'll actually graph the true function in blue here. So everything that's already positive still remains positive. Nothing's wrong with that. But here, so what I've done here is I've taken the y values that were normally below the x-axis and broke that branch there basically and rotated it up. This is a graph of the absolute value of log base 2 of x minus 3 plus 1. Same exact function, just instead of reflecting it about this red vertical asymptote, we are actually rotating the negative y values about the x-axis. And by the way, it's about the x-axis because you're applying the absolute value in the very end. It would be completely different if it was, actually, let me leave that there. It'd be completely different if you were asked to graph the absolute value of log base 2 of x minus 3 and absolute value and then plus 1. That's different. That just means I'm going to graph log base 2 of x minus 3, which would look something like that. And then you would take the absolute value of that function, and then you would lift that picture up 1 unit. So you can see there's a slight difference between those two, because the first one, the one we were asked to work on right now, says graph that function first. All the shifts and everything. Just get that done, then take the absolute value. The second one is saying, no, graph the function, but not all the shifts. Take the absolute value of that, and then finally apply the last shift. So you have to be able to read mathematics in the right order. This last example is really a nice example. It's not super common, but it is important that you're able to graph this logarithmic function or know that you can graph it easily. A lot of people will stare at this. Honestly, a lot of people, like instructors even, will stare at this and go, you can't graph that by hand. You totally can graph this by hand. It just requires you to do algebra before you do your trig, before you do your pre-calculus. And what is the algebra? The simple algebra that you learned way back when? Factoring. You could factor that x squared plus 10x plus 25 into x plus 5 quantity squared. Now you can use a property of logarithms that says, hey, if that's all raised to the second power, you can move that power outside. And you get this. And now, this is just a simple vertical stretch of a natural logarithmic graph shifted 5 units to the left. And so a very quick sketch of that looks like the following. Here's my vertical asymptote at x equals a -5. And otherwise, it's just going to be a stretched version of the logarithm. All the y values are twice what they used to be. So this point right here, instead of being at 1, 0, it's at -4, 0. And instead of being at e, 1, we have the point at e minus 5, 2, because it's been multiplied by 2. So e minus 5, 2. The y value, again, if you had drawn this out slowly, you know the 2 points that we would normally graph would be 1, 0 and e, 1, as the natural log of e is just 1. You're going to shift the x values 5 units to the right, so you're subtracting 5 from all of them, and you're doubling the y values. That's why it's e minus 5, 2. The very fast way of doing that problem. I don't want to try to convince you that this is super common, but using properties of logarithms like this is very important. So I highly recommend you study that example.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much, that isn't kosher. You may really hurt inside. The doesn't justify you to speak too loud and cry.